Welcome to lesson 4.3. Lesson 4.3, we're going to kind of shift gears a little bit. We've been talking about graphing quadratic functions, and in graphing quadratic functions, we've been spending, again, a little bit of time talking about like where are their intercepts, where is the axis of symmetry, and some of that kind of stuff. So we're going to change gears just a little bit. We're going to talk a little bit about solving quadratic equations, specifically when these quadratic equations are equal to 0. Now, I want you to take special note of this. The leading coefficient in any of these problems that we're going to be talking about in 4.3 is a 1. When we start getting into the next lesson in 4.4, I'm going to give you a little bit different methodology, same concept, but a little different methodology that you'll have to fall back on when that number is not 1. But moving ahead then, let's just kind of talk about some terminology then. First of all, a monomial. Monomial is an expression that is either a number, a variable, or the product of a number and one or more variables. So things like, 2x, a constant can be a monomial. Let's see, 4x squared. You can also have things like the product of a couple of variables too, but all of these terms all by themselves are considered a monomial. Now, if I had the sum of a couple of these, then I could have something like 2x plus 5. That happens to be a binomial because it's the sum of two monomials. A trinomial is the sum of three monomials. So 2x squared minus 4x plus 7. You might say, well, wait a minute, Mr. Lowe, it said sum here. Remember that we can write all subtracts as plus and minus. Now it is actually a sum of three monomial terms, where now the 4x is actually a negative 4x. All right, we already have this definition. A quadratic equation is any equation that can be written in the form ax squared plus bx plus c equals 0, where a is not equal to 0. And then again, the key term here is that it has an x squared term in it as long as that leading coefficient is not a 0. All of this really means the exact same thing. The root of an equation is a solution of a quadratic equation. So some solution to, again, this equation up here. Whatever number makes that equal to 0 is considered to be a root of that equation, a solution to that quadratic function. And so we move on, we talk about the zeros of a function, again, numbers p and q in the function in intercept form that are also called the zeros of the function. So if you remember, intercept form was this guy here, x minus p times x minus q, and so my two zeros of that function are p and q because those are the values. When I plug in those values, I get 0 for the function. So as you can see, those are really the same kind of thing as a root of an equation. All right, so let's just get right to it then, taking a look then at factoring. Now, when we want to go ahead and factor a trinomial, factoring a trinomial in the form x squared plus bx plus c, essentially factoring is what we really, in a trinomial such as this, we're trying to undo FOIL. Okay, and if you remember, we talked about FOIL. FOIL is multiplying first outers inners last. We reviewed that in lesson 4.1. And so, I'm sorry, 4.2. And so to undo FOIL is to factor. And so we want to rewrite this trinomial here, x squared plus 7x minus 7, as the product of two things, x plus m and x plus n, where the product of m and n is equal to negative 8. And the sum of those is equal to 7. Now you might say, well, why is that? Well, remember, if I have an x here and an x here, I want to come up with two numbers, m and n, and we used p and q before, but I want to come up with two numbers where when I multiply them together, I get this last term here, because remember, when you do first, outsides, insides, last, the last is going to give us our constant on the end. So in this case, when I do the L in FOIL, that's going to give me a negative 8. All right? Now, when I do the outsides and insides, I know what first is going to give me. X times x is going to give me the x squared here. All right? But when I multiply the outsides, x times n, and the insides, which is m times x, so you're going to get mx plus nx, and so those two together will essentially become m plus n times x. So the sum of whatever these numbers are, whatever these two numbers are, the sum of those two is going to give me this middle term here. All right, now, I don't subscribe to this, so I'm going to slide this right out of here. I don't even want you guys to fill this in at all. In fact, we're going to try it over here. We're going to just kind of write a skeleton of a FOIL statement. Okay, we want to write the product of two binomials, where I know the first term is x and x, because when I do the firsts, the f, I'm going to get x squared, which is what I want. Now, when you do the o and the I, Okay, I don't know what these two terms are going to be, but I know altogether, I know I'm going to get 7x, and specifically positive 7x. Now when I get the L on the end, that's the last term. That's going to be two numbers that multiply together to make negative 8. Now let's think about products of positives and negative numbers. The only way I'm going to get negative 8 is if these two numbers are one's positive and one's negative, because the product of a positive and a negative is going to give you negative. If these were both positives, say positive and positive, I would get positive 8, and that's not what I want. If they were both negatives, okay, suppose this was a negative sign instead. If this was negative and negative, now a negative times a negative is going to give me, again, positive 8, which is not what I want. So what we're going to do is we're going to say, look, we can do a positive and a negative to get negative 8. And you get better at this the more we practice with this. All right? Now, somebody always asks me every year, does it matter which order they're in? Not at all, because again, remember that multiplication is commutative, so you could have the x minus first and the x plus second, as long as the right number goes with which, and you'll know what I mean when we get to that in a second. So we need two numbers that multiply to negative 8. Okay, two numbers, m times n, that multiply to negative 8. And the product of those two has to be negative 8, but their sum has to be positive 7. Well, two numbers that multiply to negative 8 that add to positive 7 are 8 and 1. Because now when I do the x times x, I'm going to get my x squared. When I do x times negative 1, I'm going to get negative 1x. And when I do 8 times x, I'm going to get positive 8x. And when I add those two together, guess what I get? 7x. And on the end, positive 8 times negative 1 becomes my negative 8. And so notice that m is equal to, we'll just say m is equal to 8, n equals negative 1. So then my products are x plus 8 and x minus 1. All right? Now, at the top of the next page, we start getting into this idea of these special factoring patterns. And special factoring patterns are really helpful if you can memorize them. You can factor any problem, any product like this kind of without. Again, these patterns are helpful. They're certainly not the end-all be-all, but they're definitely helpful when you go to factor some things here. And so some of these are special, again, special factoring patterns. They only work in special circumstances. So we're going to start with a squared minus b squared. Well, a squared minus b squared is really a minus b times a plus b. And the reason for that is if you FOIL this back out, a minus b times a plus b. If I FOIL this back out, I do a times a and get a squared. A times b, which is positive ab. B, negative b times a, and I'm going to write that as negative ab, not negative ba, it's the same thing. And then negative b times positive b becomes negative b squared. Now what happens to these middle two terms? Well, they're opposites, and so they cancel out. And so you can see that if I FOIL a minus b times a plus b, I get the difference of two perfect squares. So an example of that would be x squared minus 4 is equal to x plus 2 and x minus 2, because what did I square to get x? I squared x. What did I square to get 4? I squared 2, and so that's where your numbers come from. Notice for difference of squares pattern, you should have one of each. And we'll use the highlighter so you can see that there's one of each there in that particular case. A perfect square trinomial there are two different cases. One of them is when you have a plus here. If it's a squared plus twice the product of a and b squared, that's the same thing as a plus b quantity squared. All right, so an example of that would be x squared plus 6x plus 9. Again, how we do this, we say, what did we square to get x squared? We squared x. What did we square to get 9? We squared 3. And take a look, if I FOIL out x plus 3 times x plus 3, remember this is the product of these two, simply not squaring both here and here. All right, so when I FOIL this, I get x squared plus, and then x times 3 is 3x. 3 times x is another 3x, and then 3 times 3 is 9. And so those two add together to give you the 6x here, and that's why that works. All right. So again, this middle term is the product of 2 times twice 3 times x, because what did I square to get 9? I squared 3. What did I square to get x squared? I squared x. 3 times x is 3x. Doubled is 6x. That's that middle term. All right, and if it's a squared minus 2ab, you might imagine this is then a minus b quantity squared. So those, again, are just a couple of examples of some special factoring patterns that we may or may not be able to use in a lot of our factoring problems. So let's take a look at factoring a few problems in example 2 with special patterns. Notice that the first example we start with is x squared minus 25, and you can see that it's just the difference of two things that are perfect squares. Well, as you might imagine, we might use the pattern here, difference of two squares. This is simply x squared minus 25, which is the same thing as x squared minus 5 squared. You can see it's the difference of two things that are perfect squares. So according to the pattern, this is then x plus 5 and x minus 5. And again, it's completely irrelevant which order you do them. That would be fine. Now, in letter B, I can see that this is a perfect square and this is a perfect square. All right? And the perfect square then is 11 squared, right? Because 11 times 11 is going to give me 121. So that middle term then, notice the middle term is twice 11 times m, right? So this is 2 times m times 11, and since that middle term is twice the product of the first term and the last term, without the squares on them, all right, then I know that this is the same thing as m minus 11 squared. All right, again, the whole thing squared. So again, that's just the difference of a perfect square trinomial when it's the difference. All right, so again, those patterns are going to come into play as you take a look at some of these problems. The patterns will kind of show themselves as you use them. So let's try a couple checkpoint problems. The first one is not a special pattern. The second one is. See if you can use those ideas to help you solve the first two examples here. All right, so getting back to our patterns here, our factoring here. Remember, we're trying to undo FOIL, so I need to find two numbers that multiply to positive 12 that add to 7. Now, some of you guys are way ahead of me and can do this, and you're just fine, but if you need some more instruction here, let's think about this being a positive 12. And so the only way I'm going to get positive 12 is if these two signs are matching, right? These have to match. Either they're both pluses or they're both minuses. The only way we're going to get positive 12 is if I do a negative times a negative or a positive times a positive. Now, how am I going to get positive 7x out of double negatives? Well, you can't, right? So that means that these both have to be pluses. Now let's think about factors of 12. You got 1 and 12, 2 and 6, 3 and 4. Again, when they're both positives, and you can put positives with them if you need to, all right, which one of those products is going to give us 12, but then add to 7? Well, that's 3 and 4, and so this is 3 and 4. So we're going to go ahead and make that as x plus 3 times x plus 4. And again, you can always check by FOIL. All right, so if we check by FOIL, again, you get x times x, which is x squared. X times 4, 4x. 3 times x is another 3x, so that's 7x, and then 3 times 4 is 12. So we're good. Number 2 is the difference of two things that are perfect squares. We see that this is the same thing as x squared minus 9 squared. And so if it's the difference of two perfect squares, this is x plus 9 times x minus 9. And again, you can check by foiling. X times x gives you the x squared. X times negative 9 is negative 9x. Positive 9 times x is positive 9x. And so those two middle terms are going to cancel out. 9 times negative 9 is your negative 81. All right, so let's get into this idea of called the zero product property. And I think the zero product property is probably one of the more powerful things that we'll use. So for those of you guys that are kind of half tuned out right now, this is a big idea. We will use this a lot in this chapter. In words, it says, if the product of two expressions is equal to 0, then either one or both of the expressions has to equal 0. So algebraically, we're saying if a and b are expressions and the product of a and b is 0, then either a is 0 or b is 0, or potentially both of them are 0. So what is that for? Why in the heck would we even care about talking about this idea of the zero product property? Well, we've just been taking things. If you look at example checkpoint number 1 from above, we just factored this into x plus 3 times x minus 3. I'm sorry, we did not. It was x plus 3. Sorry, my pen's kind of bugging with me here. X plus 3 times x plus 4. And so what if I gave you x squared plus 7x plus 12 is equal to 0, and I asked you to solve that equation for the values of x, or for what we call the roots of the equation, or the zeros of the function, like we talked about in our two definitions from before. Well, if I could write this as the product of two things is equal to 0, then I know that either this is 0 or this is 0. Okay, so an example of that would be something like this, and hopefully you're looking at this and saying, man, that's kind of like that intercept form from last section, all right? But this is x plus 5 times x plus 2 is equal to 0. Well, then I know that either x plus 5 is 0 or x plus 2 is 0. All right? And so to solve this equation, x plus 5 is equal to 0, please don't say x equals 5. We'd have to take away 5 from both sides. I get x equals negative 5. And for the same reason, the other one would be negative 2. All right, so when we talk about finding the roots of an equation, that's exactly what we were just discussing from before. It says find the roots of the equation x squared minus 2x minus 15 equals 0. So again, the roots, the solutions, all right, the zeros, whatever. All of these mean the exact same thing. Talking about the exact same thing. So x squared minus 2x minus 15. We need to find two numbers that multiply, and I'm just going to make a chart. They need to multiply to make negative 15, and they need to add to make negative 2. All right, we need to multiply to make negative 15 and add to make negative 2. So let's think about factors of 15, like 1 and 15, and really 3 and 5. Those are my only pairs that work to multiply to negative 15. All right, now the only way I'm going to get negative 15 is if these signs don't match. I'm going to have one of each, right? One of each. So I got to have one of each sign, otherwise I'm never going to get to negative 15. So I'm going to say x plus and x minus, and it doesn't matter what order we put them in. But I have to have one of each because otherwise I'm never going to get negative 15. Now let's think a little bit about what those numbers are. Well, if I do, for example, positive 1 and negative 15, that's going to give me negative 14 when I add them together. So again, we're looking for two numbers that are actually going to be subtracted, because if I have one of each, I'm going to be taking the difference, right? And so I need the difference of those two numbers to be negative 2. Well, that makes sense that this is then positive 3 and negative 5, because positive 3 plus negative 5 gives me negative 2. So that's my pairing right there, x plus 3 and x minus 5. And again, if you're not sure, you can always check. This is x squared. Okay, this is negative 5x. This is positive 3x, which makes your negative 2x in the middle, and negative 15. So we should be in good shape there. All right, so again, we still have the 3 and the negative 5. So then we have x plus 3 is equal to 0, or x minus 5 is equal to 0. All right, by the zero product property, it says if the product of these two things is 0, then one or both of them is 0, so set them both equal to 0. Solving this equation here, you simply subtract 3 from both sides, you get x equals negative 3, or x equals positive 5. So my zeros, or my roots, are negative 3 and 5. All right, so sliding over to our next example. Again, and I kind of like this table format, so I'd like to see you guys continue to use this table format here. Again, we want to find the zeros of the function, which is the same thing we just did. Find out when does this thing equal 0. Okay? So we want to say, when does this thing equal 0? So replace the y with a 0 and solve. So I need two numbers that multiply to negative 6 that add to positive 5. Let's think about the factors of negative 6 here. Well, to get 6, we got 1 and 6 and 2 and 3. Now, you got to be real careful with this one because the signs are kind of goofy here. We need a negative 6 as a product. We need negative 6 as a product. So what does that tell us about our signs? Well, again, because this is negative 6, that means again that I need one of each. Okay, if I have two positives, if I had two positives here, I would never get negative 6. If I had two negatives, I'd never get negative 6. So the first thing is we have to address that this is going to be x plus and x minus. And again, it doesn't matter which order you put them in. I just put the positive first for simplification. All right. Now I'm looking at 2 and 3 and saying, well, 2 plus 3, well, that's equal to 5. But what if one was positive and one was negative? Well, I'm either going to get positive 1 or negative 1 if I switch the signs around, make this positive and this negative. So those two are not the right pairing. I need a one of each where they add up to positive 5 but multiply to negative 6. Well, what if I did this? Negative 1 and positive 6, well, those multiply to negative 6, but they do add to positive 5. And so I need positive 6 and negative 1. And so the zeros of the function are negative 6 and positive 1. Now, again, realize that the signs got flip-flopped, all right, because the zero product property says that x plus 6 is equal to 0 or x minus 1 is equal to 0. And so when I solve this equation, I have to minus 6 from both sides, I get negative 6. Add 1 to both sides, I get x equals positive 1. All right, now, before I get into the graph, I want you guys to remember that from last section, we talked about this, y equals x minus p, x minus q, where p and q are my zeros of the solution, where this thing is equal to 0. The x-intercepts were equal to p and q. Well, hopefully this is starting to come together a little bit for you, because in the last section we already had it factored. We said the product of these two things factored is equal to 0, so either p equals 0, p is a solution, or q is a solution, and we did the opposite of whatever was in here. So if it said x plus 2 is a factor, then negative 2 is a solution. All right, so we did that last section. Again, hopefully you're recognizing the fact that that's why we flip-flop the signs, is because of this zero product property. All right, now it says to check it on a graph, and again, you're more than welcome to do that. You can certainly plug in to your graphing calculator, y equals, and plug in x squared plus 5x minus 6, and then go ahead and graph it. And you'll see there that we have zeros at positive 1. Whoops. We have zeros at positive 1 and negative 5. And so that's what you should have down on the previous page. All right? Now, the graphing calculator is not necessarily a means for solution, although it does help you to find some of those solutions. It helps you get an idea of where they might be, but definitely you don't want to just get in the habit of plugging them into your graphing calculator, because they don't always work very pretty, especially when we get into the next lesson. So find all roots of the equation. Basically, again, find out the values of x that make this thing 0. And so again, we need an x and an x. We need two numbers that multiply to make positive 2 that add to make negative 3. Well, 2's only got two factors, 1 and 2. And we know that both of these have got to be negative and negative. All right? And again, why do I know they're double negatives? Because the only way I'm going to get positive 2 is if these two signs are both the same. But if I do double positives, I'm never going to get the negative 3x that I want. So it's negative 2 and negative 1. Product of those two, x minus 2 and x minus 1 equals 0. So either x equals 2 or x equals 1. So again, you switch the signs of the factors because of the zero product property. Find the zeros of the function. Again, when does this thing equal 0? Now this one's a little trickier because we got lots more factors of 40. But I need two numbers that multiply to negative 40 that add to make 3. So factors of 40 are like 1 and 40, 2 and 20, 4 and 10, and 5 and 8. So those are all my factor pairings that multiply to make 40. Now again, to get negative 40, hopefully you guys are recognizing this by now. How are we going to get negative 40? Well, if I have one of each. So I'm going to have a plus and a minus. And so now I need two numbers that have opposite signs that add to 3. Right, there we go. Negative 5 and positive 8 are going to give me positive 3, so that's my set. Positive 8, negative 5 is equal to 0. And so my zeros of the function are then x equals negative 8 and x equals positive 5.